Is the application to Le Chatelier's principle for this section. So sort of similar to the end of solubility equilibrium where we talked about whether precipitate forms. This is going to look at how a buffer can work to relieve a stress on acid-base equilibrium. So when you might have used the word buffer to describe somebody who, you know, helps to diffuse a situation. They're sort of neutral. So the same thing in their temperament, the same sort of idea occurs with a buffer. When you have a buffer, and we're going to talk about buffer notation, so it looks very different from what we've been doing before. So every buffer is a mixture. There has to be some acid and its conjugate base, or the base and its conjugate acid, so that when you add an acid or base to it as a stress, then you're going to minimize the change in pH. So the buffer in our blood helps to prevent our pH from changing too quickly, making us sick or being fatal. Okay? And so you can have equal molar concentrations of both, or pretty similar, like almost equal, and that will work enough. Should you continue in chemistry in university, you can calculate the buffer capacity. We're going to do titration tomorrow, the lesson tomorrow, and we'll look at making a titration curve and where visually, graphically, where you can see if a solution is going to the pH range for its buffer capacity, but that's not really what we're going to do this year. Okay, so we're going to use something called the Henderson-Hasselbalch equation, and this is for buffers only. So yesterday, when we wrote dissociation equations, whether it was acidic or basic, the ion concentration was 0. Today, that is not going to be true. So we are going to calculate the new pH using the concentration of the anion and the acid, or if you have a base, the concentration of the cation with the original base. So just like yesterday, we're going to find POH. So whenever you have a basic question, there's always going to be an extra step. You're always going to have to change POH into pH. And so Henderson and Hasselbalch are scientists who discovered that this relationship will work for a buffer because there is concentrations of the original solution and its conjugate. When you use the Henderson-Hasselbalch equation, we have to use something called pKa and pKb. So Ka would be like 1.8 times 10 to the negative 5. That is not very similar to the pH scale of like 2.38. So the P means in pH is like negative log of the hydrogen ion concentration. So the same thing for pKa, that would be negative log Ka. Okay, which makes it a comparable quantity and a little bit easier to analyze than the tiny value for Ka or Kb. So these questions usually say the word for a buffer, blah, blah, blah. They will have the buffer notation with the semicolon. You'll be given a Ka, so there's lots, or Kb, there's lots of clues about what you're trying to do in this question. The hardest part is that you need to use, not the hardest part, but the application part to this is using Le Chatelier's principle to figure out which direction the shift is. And these two versions of this formula will be on the formula sheet. Yes. No, we're going to do it another way. You'll see. Okay. Another thing as well, if you don't have a lot of experience with logs and using the log button on your calculator, this needs to be divided. The concentration needs to be divided first. So some calculators automatically, when you push log, they will pull up brackets and some don't. So again, you need to know how your calculator works. So if you use one like the Casio FX300ES, it pulls up the brackets automatically. I don't know about the AP Calculus one, so you'll have to check. Or just do the division first and then take the log of that number. Because those of you that have taken advanced functions, the log of a divided number is a log law, so it will mess up your calculator if it doesn't do brackets. We'll do log of the one number and log of the other number instead of the log of the answer to the division. Okay, so the principles of buffer systems follow Le Chatelier's principle, and so each buffer has to be a weak substance. So you're going to see the same solutions like we did yesterday, the COOH, for a base, the NH. So again, hopefully by the end of the unit, you're sort of used to that notation. And then we're going to add two possible stresses, either an acid or a strong base, which will be OH. If you don't do a strong substance as the stress, then you kind of have to do ice twice, which is a lot more math and a lot more of analysis you can do within 75 minutes, including other questions. So we'll just stick to a strong acid, strong base stress. Okay, so I think it says that. Somewhere. You know what, we'll write it here. Okay, so the stress is going to be a strong acid, strong base. So you can use the idea that there is 100% dissociation. So if you have HCl, the concentration's 0.1, the concentration of H plus will be 0.1. If you add, say, sodium hydroxide, the concentration's 0.1, so would the hydroxide, okay? To make our life easier. So yesterday, then, we said that initially the concentration of ions is 0. So if you have a shift if the concentration was 0, then you would have a huge shift and a huge impact on the pH, which isn't good. So then if the concentration of both sides is approximately equal, then a shift in either direction is not going to be as drastic, and the change in pH won't be either. So what we're going to do when we do the calculation, most of the questions will be find the initial, figure out what the stress is, find after the stress what happens to concentration, and calculate change in pH, like pH 2 minus pH 1. Okay? So these two slides have what happens when you have an acidic buffer, and then we'll do a basic buffer, because this is sort of similar to the Le Chatelier lab. If you have an acid and you add hydrogen, it's obvious where the stress is. If you add hydroxide, there is no hydroxide here. So again, you have to think about what happens. But it's very similar to what we've done before. So when you have a buffer, you have the weak acid. and its conjugate base. So unlike yesterday, the initials will not be 0 in our ice table. Okay, so if we add acid, which is a source of hydrogen ions, then that is going to be the stress. You're increasing the hydrogen ion concentration. So for the effect, decide, again, it's the same Le Chatelier's principle, so decide to write the effect however you did it before. Do you like to think of it like that means if it's a product you're increasing, then the reactant has to increase to balance out? Maybe you prefer to say, because this isn't a very big space, but maybe you prefer to say if you increase the concentration of H+, it has to shift to consume it. Whatever made more sense to you in the first unit will work here too, okay? Okay, so either way, shifts to consume the product or shifts to make more reactant, that's a shift left or reverse. Yes. Mm-hmm. And I included this last point only because, like the solubility equilibrium, we did this, Le Chatelier shifting, and then we had to say whether a precipitate was going to form. So the effect on the pH is really like the final application step. What we're going to do is calculate change in pH. So sometimes the delta pH will be negative, and sometimes it will be positive. And you don't really have to stress about that necessarily. And even writing the effect on pH can be tricky because if a pH decreases, then that's actually more acidic. If a pH increases, it's less acidic. So that can seem weird too. But when you add an acid, the pH is going to decrease and become more acidic, but in a buffer solution, which is what you would expect, but in a buffer solution, it won't be as drastic, okay? So small decrease. So when you calculate the change in pH, if you get a negative number, that's not a big deal. So now we're adding the opposite type of solution to our weak acid buffer. And, you know, I wanted to use this clever little beaker, but this equation is truncated. So I took out the water like we did yesterday where I crossed it out of the ice table. Again, just like the Le Chatelier lab, you can think of this two ways. If you add OH to a solution that has H+, what are you going to make? You're going to make water, it's neutralization, or, so there's going to be an increase in water, which is a reactant, or if you react H and OH, then technically the hydrogen ion concentration is being decreased, so the system has to shift to replace it. Either way, it's going to be a shift to the right. So, whatever explanation you preferred before, you can use again. Okay, so now we have a buffer, which is a weak base. And it's conjugate acid. And so all the things that we did yesterday, if you're given a KB, then it's basic. A Ka would be acidic. I left the water out, but you can add it in there to figure out the shift if that helps. Okay, so now again, whichever one is the opposite type of stress you're adding, then you have to consider that water is being produced or neutralization is occurring, where the similar type of solution, so if you add a base to a basic buffer, then you're going to increase something that's right in the formula. So that is the beauty of a buffer. It doesn't matter which stress you use. It doesn't matter if you have an acid and you add a basic stress or a base and you add an acid stress, it can deal with it, okay? All right, the same way. But even the effect of the stress is very similar. Water is always a reactant. The ion that's important, like we talked about yesterday, the OH or the H, is always on the product side. So if you get rid of the H or the OH, it has to shift right to make more, or shift right to consume, or forward to consume the H2O. So these questions are very similar. So then when you add a base to a base buffer, then the OH is in the equation. So you're directly increasing a product. So it shifts away from the product or shifts to increase the reactants to balance out. Again, whatever you used last time will work here, whatever explanation. Let's see what I wrote over here. Okay, so we are going to calculate the pH of a buffer. So I formatted this example where we calculate the pH of the buffer. Then we're going to do a stress. Sometimes the questions are more like the last one we're going to do where it's all kind of combined. So we're going to do both. Okay, and I just realized I put the Ka in example 2, not in example 1, but that's okay. I'm just going to copy it. So this would still, just like yesterday, is a reference value. Okay, so when you do today's homework, again, your textbook probably wants you to go and look it up. So it says calculate the pH of a 0.1 molar CH3COOH, CH3COO negative. So this is an acid. And its conjugate base. Even if you forgot that it was COOH, it tells you the Ka, A's for acid. It tells you that it's a buffer, which means that we can use the Henderson-Hasselbalch equation. But it also gives you this weird sort of notation. Really, technically, this is telling you what the original solution is and what the conjugate is. So it actually makes your life a little bit easier. Now you don't have to figure out what that other ion should be. You just need to figure out if it's going to be H plus or H3O plus or OH. Okay? So when you have buffer notation like this, and it says 0.1 molar, that means that you have 0.1 molar acid. That is a terrible arrow. And base, okay? So that's what this colon is telling us, different from yesterday. So when you write the equation, now it tells me what the conjugate should be. Okay, and then this is an acid because of the Ka. It has donated its proton to water. So even if chemically you forget that, and then you're like, okay, buffer, Henderson-Hasselbalch equation. If you go and try to use the Henderson-Hasselbalch equation, can you do log 0? No, your calculator will say math error. So then hopefully, even if you never took advanced functions, your calculator won't let you do it. And then you'll be like, oh shoot, this is a buffer. I have to put in 2 concentrations, okay? Okay, so the Henderson-Hasselbalch equation does need us to do pKa. It is a pretty straightforward calculation, so you can show your work or you can just put the answer into the formula. It's up to you. Again, be careful of how you do scientific notation as well as logs in your calculator. You do not want to do negative log. If you type in 1.8 times 10 to the power of negative 5, your calculator will do negative log of 1.8 and then multiply by 10 to the negative 5, which is going to mess up your answer. Hopefully you are using EXP or EE or some way that your calculator does scientific notation for you. Then it's showing that it's a whole number, or you have to use brackets, okay? One annoying thing is, okay, so pKa, this sort of makes sense. This is on the acidic side. We have an acidic buffer. When you do the basic pKb, you're actually also going to get a low number, which is annoying because then you're like, wait a minute, aren't acids on the high end of a logarithmic scale? But remember, we are going to do pOH and then we're going to switch it. So not that you need to switch it for pKb, but in your brain, sort of be thinking like that. So it is going to look very similar, whether it's an acid or a base, just based on your calculator. When you type in negative log, it has no idea what type of solution you're using. So when you do an acid, use the pH form of Henderson-Hasselbalch. When you have a base, do the pOH form, okay? So now, plug it in. If the concentrations are the same, the log of 1 is 0. That's okay. That is the log law, which maybe you will know. Definitely one of the questions on the review, it's not exactly the same, but when it is the same, then again, mathematically, you can follow those laws or just type it in your calculator, okay? So this question, all we had to do was find the pH. That was it, okay? No stresses. But then the next two questions are going to have stresses applied. Sometimes this will be part 1 or part A, calculate the pH before, and then part B will do what's the stress. It just depends on the question. So I tried to form or write the examples both ways so that when you go to do the homework, you'll see in case your textbook is a little bit different. Okay, so this question says calculate the change in pH. So sometimes it's not always A and B, but in order to do the change in pH, that means you need, just like delta T, whether it was time or temperature, the change in the moles of gas, you always need something to subtract. So you need a before stress and then an after stress. Sometimes it'll ask you to calculate concentration like this one does. Sometimes it doesn't. Okay, so you just have to read and look at the question and what you're given. Okay, so technically this solution, 0.1 molar, that's the one that we just did. Okay, so I'm going to use I don't want to do it again. So I'm going to use the before pH as the one we just found. So that first question, yes, we had to find pKa, but really we were already given the 0.1. That question would be probably out of like 2 marks. This question is going to be a considerable, there's much more work. I think the notes organized in 2 columns. So you can do, if you would like example 2 on the left and example 4 on the right, okay? Or sorry, example 2 and then example 3 on the right. If you would like to organize your note that way. Okay, so when we figure out how the equilibrium is going to shift when you add a stress, then when we do equilibrium, of course we need to do ice. When we do ice, then the value we put into an ice table is molar. So here I've chosen to give you this as moles and milliliters, so we have to find concentration first. You won't always have to do that, okay? So again, just read the question carefully. Okay, so just check. Am I given concentration or not? So sometimes you'll have to do this step and sometimes you won't, okay? Yes. Yes. So now we have to decide how this acid is going to affect our equilibrium. So there are a couple of things that are sort of background that you don't have to worry about. But so on this example, I'm going to write down the notes for it. But moving forward, you can just assume this is going to work every time. Okay? So as I said, the stress we're going to add, so in this case is HCl. HCl is a strong acid, and it will always be strong acid or strong base. Okay? And strong acids have 100% dissociation. So if this is 0.1, so is this. Okay, so you can just assume this is going to work every time. You don't need to write another equation for the stress unless you want to. And there are more notes you can write if you would like. Okay, so why does it matter where the stress goes? So remember, we're thinking about what this is going to be in dissociation. Okay, so just like yesterday, you always need a dissociation equation. And initially, we have 0.1 molar acetic acid and its conjugate base. But here's the thing. When we do the Henderson-Hasselbalch equation, unlike pH, so yesterday, the hydrogen ion or H3O plus concentration was very important. Today, I'm just going to skip back for 2 seconds. When we're doing a buffer, we care about the anion and the acid. So we're going to modify or simplify our ice table, okay? So this is the stress, the H3O plus or the H plus. That means that whatever you add has to be consumed, right? We just said that. So that means that we sort of know how much our equilibrium needs to change by, which is not something that we have done before. So we are adding 0.01 H3O plus, and our solution needs to consume the entire amount. So again, just like yesterday, we're only going to do 1 to 1 to 1 to 1. So this is a coefficient of 1, so is this, okay? So if it wasn't, then you would have to do stoichiometry before you could do this, and it's just more math that we can do in a reasonable amount of time in high school, okay? Actually, yeah. So you can do the same thing as yesterday, cross out the water, but we're really sort of modifying ice for only the information we need to do the Henderson-Hasselbalch. So if you increase a product, the system has to shift to consume it. So if it shifts to consume this, then this is going to go down and this is going to go up, right? We just said it's going to shift to the left. If this is how much needs to be consumed, then we know how much it's going to change by. Okay, so it shifts left to consume the added product. So then this is another sort of background thing. There is definitely a buffer capacity. You can't just put in 3 liters of strong acid and expect your buffer to work, okay? So the number that you subtract by or add by should be less than the initial number, which I will have made sure works. So if you calculate the concentration wrong and you don't get a number that's smaller, then go back and fix it, okay? Because just like last time, we don't want a negative. So 0.1 minus 0.01 is 0.09. 0.1 plus 0.01 is 0.11. So after the stress has been added, the concentration has been changed, and we need to recalculate pH. So buffers are unique because you know how much you want to use up. And we're sort of simplifying the ice table because when we use the Henderson-Hasselbalch equation, then we are only worried about the anion and the concentration of the acid. You can do this using a full ice table, using the Ka value, writing the equilibrium law. You can definitely do that. It's just more work. So we have a before pH or pH initial. We need a final pH. So we've calculated the new concentrations, and then I'm going to calculate a new pH. The pKa value will be the same. That's sort of like, it's almost like a reference value. Sometimes actually textbooks won't even give you the Ka value. They'll give you the pKa because it's a little bit more useful, a little bit more comparable because it looks like a pH value. Just depends. Okay, so I just don't want to squish. So now we're going to do the after the stress. Okay, so the pH before was 4.74. If you add an acid, should it go down a little bit? Yes, it should. Did it go down a lot? No, it didn't, which is good. That's what a buffer should do. And if you leave out the negative sign, it actually doesn't matter. You're just looking for how much did it change by. It did not change by very much. That's what we want. So the next example, I'm going to write less notes, okay? So I'll just do more of the math because, again, the behind the scenes should work every time. It's going to be a strong acid that we add, so it's going to be whatever that concentration is will be what the H plus is. You should get a number that is smaller than the initial, okay? So all that kind of stuff will work itself out. I'm not here to trick you. Okay, so now we're going to do a basic buffer. So again, it says KB. It's got the NH. So whatever way you like to remember yesterday is the same as today. But again, a buffer will give you both. So it tells you in the question what the formula of the base is, as well as its conjugate acid. So it actually makes your life a little bit easier. So this question, it just says to do the change in pH. So we need to do the before and the after. And then whenever you have a base, again, just like yesterday, you're always going to have an extra calculation, okay? Because we don't deal with a pOH scale. Okay, so what can we do? We can do the pKb. We can do the before pH pretty simply. And we could calculate the concentration of the stress if you wanted to, or you can wait and do that after, okay? Okay, so the before pH, whether it's like part A in a question or if it's a question like this and they're combined, this is virtually everything that you're given is already or can be used. So you're given the KB, you just plug it in to pKb. The concentration is 0.2. You have to do very little sort of thinking. That's not a 6, sorry. So again, when you get your answer and you're like, wait a minute, pOH as 4.74, it's a base. That doesn't make sense. Remember, bases always have the extra calculation. And even when you do a buffer solution, you can think of the things that we talked about yesterday. Is this a very super basic pH? No, because it's weak. Okay, so all of the same ideas still apply to today. The stressful part is figuring out, is it going to shift right or left? And you still need to write your own dissociation equation. But it does give you the formula of the conjugate, so that can help maybe, hopefully. So in this situation, I gave you moles and milliliters again, moles and volume. You have to find concentration first. But again, that doesn't always happen. So just read what the question gives you. And again, we have a 0.2 molar concentration for the base and its conjugate acid. When I find the concentration of the stress, it should be less than that, okay? So if you don't get something less, then again, you can go back and check your work. Like for example, gives you it in milliliters. If you forgot to change it to liters, maybe that would mess you up. You can do the same thing that you did yesterday if you like, to really emphasize your answer, whatever. It's almost identical except the ions are not both zero this time. That's all. And then when they're not zero, then we can use the Henderson-Hasselbalch. Okay, so in the question, I'm given -3 moles. I wrote -4, sorry. Which is 0.067. So again, take a quick look. Think, is that less than 0.2? Yes, it is. So I'm probably right. We need a dissociation equation always to do ice. But use what you're given to help you. We're given the base and its conjugate formula. Put in the water or not, it's up to you. But this is a base, which means it takes the proton from water, leaving OH, which is what we did yesterday too. You're given 0.2. But now our stress is for the opposite type of solution. So again, you have two ways you can think about this. So because we are going to use the Henderson-Hasselbalch equation, we don't really care about H2O or OH. So you can think of it either way. So you can either say more water is produced or OH is decreased. So again, either way, if you decrease this, it has to shift right to make more. If you increase this, it has to shift right to use it up. So then this will increase and this will decrease in a shift right. Or forward, sorry, if you don't like right. So again, all the background information should work. It's still 1-to-1. When you do the concentration of the stress, it should be less than the initial so that when you subtract, you don't get a negative number. Okay, so all that stuff should work itself out. And now we're ready to go. Okay, so now the conjugate base, the conjugate acid, the cation has increased and the base has decreased. So our final or after pH again has gone down. It was an acidic stress. Down means more acidic. That makes sense. But again, when you do the subtracting, I don't really care which way you do it. If you ignore the negative, that doesn't really matter. We just want the buffer or the change in the pH to not be super high. Okay? Whoa. All right, so 0.3 is not that bad, not too bad.